Today's video will demonstrate how to convert text into a floating point number. Hello, I'm James Helfrich. We use floating point numbers every day, and we take it for granted that we could convert an array of, well, digits, decimals, and signs into a number the computer can do math with. Well, how exactly does that happen? Well, it turns out the compiler implements a lot of code to make this magic take place. And this video will explain what that magic is. Now, in order to store a floating point number in binary, we have to remind ourselves how the IEEE 754 format works. So there's basically three fields. There's the sign bit, the exponent field, and the significant field. And each one of these can be of different sizes depending upon the size of our floating point number. These three fields are combined in the following format. The real number equals -1 times the sign, which is the Boolean, true or false, plus 0.1 times the trailing significant field, which is called the significand, times 2 to the exponent. Now, the exponent is stored in something called the exponent bias, which is the bias plus the exponent. And this is a signed integer similar to 2's complement, but a little bit different. And the significand is stored in something called the trailing significant field. It's a fixed point notation where the decimal point is one spot to the right of the most significant bit. Now, since the most significant bit is always 1, we can omit that, and it's basically all the decimal digits to the right of the decimal point. Now, when we convert a string into a floating point number, we go through a 7-step process. The first step is to separate the string into 3 fields: the sign, the whole number component, and the decimal point component. The second step is to compute the whole component and turn it into an unsigned integer. The third step is to compute the fractional component and turn that into a fixed point number. The fourth step is take the whole and fractional components and turn them into a single fixed point significant number. The fifth step is to convert the fixed point significant number into the trailing significant field. The sixth step is take the exponent, turn it into the exponent bias format, and finally we'll take the sign, the exponent bias, and the trailing significant field and combine those into a single floating point number. Now let's go through each one of these one at a time. Now, step 1 is to separate the input into its components. Now, I'm going to assume I have a stream. So if my stream is in a failure state, I do nothing, and I'm going to skip all the leading white spaces. So if I have a whole bunch of white spaces before the first digit, then I'm going to skip them. And then I'm going to consume the negative sign. And basically, I'm going to, if I see the negative, I'm going to remember is negative equals true. And then I'm going to skip that guy. Next, I'm going to consume all the digits. I'm going to stop if I read a decimal point or any non-digit number. I'm going to put these all into a whole digits array of integers. And then finally, if there is a period, then I'm going to consume the fractional component. I'm going to consume the period, and then as long as I still have digits, I'm going to put those into my fractional digits. All right, to demonstrate how this works, let's say my input is space negative 4285 dot 6314 space and then some other things. Now, initially, my stream pointer is pointed to the space. And so I'm going to walk through here, and as long as I have spaces, I'm going to skip through them. Now I have a negative sign. It's not a space, so I'll continue on. So negative initially equals false, but since that guy is a negative sign, then I'm going to set negative equals true. Now I'm going to move on. And I'm going to keep going as long as I have decimal digits. And I see a 4, so I'm going to add it to my whole digits. And a 2, add that, 8, add that, 5, add that. And then I have something which is not a digit, so I'll stop. So my whole digits is complete. I have an array of 4 integers, 4, 2, 8, and 5. Now, if the next guy is a dot, which it is, then I can go in here and skip that. And then I'll put everything after the dot into my fractional digits, which will be a 6 and a 3 and a 1 and a 4. And then I go to something which is not a digit. And at that point in time, I stop. Now, the output here is I have a Boolean is negative, which in this case is set to true. I have my whole digits, 4285, and I have my fractional digits, 6314. Now notice that my whole digits correspond to 10 to the third, 10 to the squared, 10 1, and 10 0. And my fractional digits correspond to 10 to the -1, 10 to the -2, 10 to the -3, and 10 to the -4. Okay, the next step is to convert the whole number into an integer. And I'm going to basically figure out how many digits I have, create that much space, and create an integer out of this. So now my 4285 base 10 becomes 1000010111101 base 2. Step 3 is to convert the fractional component into an integer. Now for a demonstration, I have a fixed point number here where I have 1 in all the binary digits, where the leftmost bit corresponds to 2 to the 6, which is 64, and then 2 to the 5, which is 32, and so on. And what I basically want to do is I want to solve for V1, V2, V3, V4, V5, corresponding to 2 to the -1, 2 to the -2, 2 to the -3, 2 to the -4. And that is this equation here. So I want to solve for V1, V2, V3, V4, V5 when on the left-hand side of the equation, I have 0.6314 base 10. All right, to demonstrate how this works, we're going to do a little bit of kind of funny math here. This will make sense in just a minute here. So I'm going to take my 0.6314 and I'm going to multiply it by 2, and that gives me 1.2628. Now, notice the left-hand side of the decimal point is a 1, and that's going to be my first bit, and the right-hand side is not yet resolved. And I'm going to bring that down. And that gives me 2 times 0.2628, and then when I multiply that together, I get 0.5256. Now, once again, 0 on the left-hand side of the decimal point is something I care about, and the right-hand side is not yet resolved. So I'm going to take that 0.5256, bring it down, multiply it by 2, and I get 1.0512. And I care about the 1, and then the rest of it's not yet resolved, so I'm going to multiply that, and that gets 0.1024, and the 0.1024, bring that down, multiply it by 2, and it comes 0.2048. And I'm going to bring that down, multiply it by 2, and it becomes 0.4096. Multiply that, becomes 0.8192. Multiply that, and it becomes 1.6384. Now, it turns out I care about these. These are the bits of my decimal points, and that becomes 101000001. And then, of course, it would go on further than that because I've not yet resolved the 0.6384 at the very bottom of my series of equations here. So the pseudocode for this is I'm going to get the significand, which is going to be in decimal, 0.6314. And then I'm going to walk through as many digits as I have to work with, as many binary digits, and that's the size of my significant field. And I'm going to take this guy and I'm going to multiply it by 2, which is the same as just adding it to itself. And then if the leftmost index is 1, I'm going to add that to my significant field. If not, I'm just going to skip it. It's going to be 0, and then I'm going to go through and set that leftmost bit to 0, and then complete the process, complete the process, complete the process. And that's going to have that iterative approach for me to find the 1 bit at a time as I walk through the algorithm. And when I'm finished, then my array of bits, in this case 101000001, is going to be my binary, is my fractional component. Okay, step 4. I'm going to combine the whole and fractional components into a single fixed point number. Let's remember my whole, which I computed earlier, is 1000010111101 base 2, and my fraction is 0.1010001, and so my significant will be the whole component plus the fractional component. All right, so the whole component is going to start at 2 to the 12, 2 to the 11, 2 to the 10, and so on. My fractional component will be 2 to the -1, -2, -3, and -4. So therefore, my significant is 1000010111101.1010001 base 2. And that's going to be for exponents set to 0. Now, we're not finished with this because we're still in a fixed point notation. We got to change this. Now, to understand how to do this, we got to understand the notion of sliding. Now, I like to turn my significant to a standard format. And to do this, we slide. Now, and to understand how this works, let's take a look at sliding with decimal numbers first. Take 1776. Now, that's the same thing as 1776 times 10 to the 0. Remember, 10 to the 0 is 1, which is the same as 177.6 times 10 to the 1, which is 10. And obviously it's true. If I multiply 10 by 177.6, I will get 1776, which is the same as 17.76 times 100, which is the same as 1.776 times 1,000. Okay, so the general formula is this. If I want to move the points to the left, then I take my significant divided by 10 and add 1 to my exponent. If I want to move to the right, I take my significant times 10 and subtract 1 from my exponent. Now, this is base 10. It turns out base 2 is the same. Let's take 2.625. That's the same thing as 2.625 times 2 to the 0, which is 1, obviously, which is the same as 5.25 times 2 to the -1, which is 1/2. So 5.25 divided by 2 is 2.625. which is the same as 10.5 divided by 4 or 21 divided by 8. So my algorithm looks the same as it did with base 10. If I want to move the decimal point to the left, I take my significant divided by 2 because we're base 2 and add 1 to my exponent. If I want to move to the right, I double my significant and subtract 1 from my exponent. Now, this is really important because when I want to convert my fixed point significant into the trailing significant field, I got to slide. So let's take a look at my trailing significant field formula here. Now, first of all, I got to figure out where the leftmost one is. So I'm going to count, I have my I leftmost is going to walk through the array until I find the leftmost one. And then I'm going to slide by that amount. And when I'm finished, then I will have my trailing significant field. So for an example, we have the number we had before, 001, 00001, 0, 1111, 01, and that was my whole component, 0.1010001, and that was my fractional component. And right now my exponent is 0. I'm multiplying this by 2 to the 0. Now I want to move my decimal point to the left, so I'm going to add 1 to my exponent. Notice how the decimal point moved. And added 1 to my exponent, it moved, add 1 to my exponent, keep on moving, keep on moving, keep on moving until I get to the most significant one. And this becomes my trailing significant field. So these correspond to 2 to 11, 2 to the 10, 2 to the 9, 2 to the 8, 2 to the 7, and so on. But there's also an implied 1 dot because the trailing significant field is all the digits to the right of the decimal point. So if I multiply 2 to the 12 plus 2 to the 7 plus 2 to the 5 plus 2 to the 4 plus 2 to the 3 plus 2 to the 2 plus 2 to the 0 plus 0.5 plus 0.0125 and so on, then I will get my original number, and you can verify that. Step 6 is to compute the exponent bias. Now, as a reminder, to compute the exponent bias, we first have to compute the bias. Now, the formula for the bias is this: 2 to the width of the exponent field minus 1 minus 1. Now, in this case, our exponent field is going to be 8 bits wide. So it's 2 to the 8 minus 1, which is 2 to the 7. 2 to the 7 minus 1, 2 to the 7 is 128. So it's 128 minus 1, and so therefore my bias will be 127. Now, my exponent bias is my bias plus my exponent. Now, my bias is 127, and my exponent was 12. Remember, as I shifted my decimal point over, as I slided it, I slid it over 12 times, so I get a 12 out of that. And therefore, it's 139 base 10. Now, 139 base 10 is 1000111 base 2. And so that's my exponent bias. Now, the final step is to combine the sign, the exponent bias, and the trailing significant field into a single floating point number. Now, as a reminder, my sign was 1 because it was negative. My exponent bias was 100001011, and that was for my previous step. And then my trailing significant field was, remember, we have the hidden 1 point, 000101111 and so on. So therefore, my floating point number will be 1 as my sign, my exponent bias, and then my trailing significant field. And that is my floating point number. Okay, let's take a look at another example. We want to convert space 42.625 space, and I want to find the binary representation where the exponent is 5 and the significant field is 10 bits in width. So first I'm going to separate the input, and so my negative field is false, my whole number is the array 4 and 2, and my fraction is the array 6 and 2 and 5. So my whole number component is going to be determined, and that's going to be 42 base 10, and then when I compute it out, it'll be 000101010. And let's verify that's true. That's 2 plus 8 plus 32, and that is in fact 42. Now my fractional part is determined, and I'm going to have 0.625. I'm going to multiply that by 2, and I get 1.25, and that 1 I'm going to retain. Take that 0.25, multiply it by 2, and I get 0.50. That 0 is retained. And I take that 0.5, multiply it by 2, and I get 1.0, and the 1 is retained. Then I take the 0, multiply it by 2, I get 0. And 0. And so my final fractional part is 10100. Now I'm going to find the significand, and then I'm going to take the whole number component plus my fractional component. I'm going to add those together, and then I'm going to find the trailing significant field by moving that decimal point over until it's 1 to the right of my most significant bit. and therefore my exponent will be 5 here, and my trailing significant field will be 0, 1, 0, 1, 0. So now I'm going to bias the exponent. So my formula is 2 to the exp minus 1. Exp is 5. 5 minus 1 is going to be 4. 2 to the 4 minus 1 is 15. And then my exponent bias is my bias plus my exponent. Well, my bias is 15 base 10. My exponent is 5 base 10. Add them together, I get 20 base 10. And that is 1, 0, 1, 0, 0. And make sure that's true. That's going to be 4 plus 16, and that is, in fact, 20. And then I'm going to combine the fields, and I'm going to have 0 because I'm positive, 1, 0, 1, 0, 0, and that's my exponent bias, and 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, and that is going to be my trailing significant field. Okay, so let's try a few problems on your own here. See if you can find the floating point representation of 85, 0.004232, pi, negative 26, negative 0.09328, and 1/3. Now, this is all going to be a standard 16-bit number, so you can look up on the internet any floating point conversion calculator to verify your results, but follow this equation and see if you can do it. This was example 0.32 in the C++ data structures textbook.